last time going over examples of using chain rule and as a side effect of that, using a lot of our individual function type derivatives because without knowing all your individual function types, it's hard to chain together, compose anything. So let me just start with a couple random examples. Chain rule looks like a mess, but if you get the general premise of it on some simpler problems, you can maybe see how to just extend that to some messier looking items, and instead of paying attention to all the details and being overwhelmed by some really horrible looking long expressions for function rules that you might have seen on some of the questions in the 150 that you've gotten. We'll take a look at some that are maybe not quite as bad for just now. You'll see some like this on there as well, but just to kind of compare the basic form, like one function versus one composed with a different one of a few basic function types. So for instance, if I had, and I don't know if I click this or not. All right, so if I had something like, here's a function that we didn't talk about in lecture before, log base 4 of x, but this is on, well, it doesn't have a 4, but it has a b or an n or something. It is on your list of things to know, rate of change function rules for. So if y, or whatever you want to call this, is log base 4 of x, what would dy dx, or y prime, be? For this, it involves a fraction, right? All the logarithms involve fractional expressions. So log base 4 of x versus the easiest one, just because of simplification, is natural log of x, which means log base e of x. The derivative of that one is just y prime equals, or dy dx equals 1 over x. So there's a bunch of different notations. You can use whatever you want, but do make sure when you're doing your mastery exam, etc., that you do name your functions something using derivative notation, the prime notation, or the d dx notation, or the r notation, whichever you prefer. But so the simplest logarithm function looking is this, but this is actually just a special case of the general logarithm rule having to do with the fact that the natural log of e is equal to 1. A natural log is a log base e, and e as a base of an exponential function. Those would be inverses to one another. But in general, logarithm functions with a base of whatever number, here's 4 as an example, the derivative of those would be 1 over x, the argument to the logarithm, or the input to the logarithm, times, in the denominator also, the natural log of 4. If you remember our exponential functions, e to the x was its own derivative. So the derivative of a function e to the x is e to the x in its function rule. If it was something else to the x, there was a times natural log of that base, natural log of a number tagged on. This comes from that. It's an inverse function. A logarithmic function is an inverse to an exponential function involving some of the same pieces. But it's got this logarithm of a number just in the denominator now instead of not in the denominator. So this is the same as 1 over x times the natural log of e. Just natural log of e is 1. So people write this, just 1 over x, for the derivative of natural log of x. So if I have something like y equals log base 17 of x, that's not any harder. It's the same pattern. The derivative, let me use r sub y notation. Let's see. R sub y of x, the rate of change of y with respect to x, is 1 over x times the natural log of 17. It's always a natural log of a number that gets tagged on in these. It's not a natural log of a variable. We started out with logs of variables. So if I just alter these a little bit, oops, maybe they'll let me pick. So if I have something like, instead of log base 4 of x, if I have y equals log base 4 of 7x squared minus 6x plus 1, which granted is going to have some weird domain in order to make this defined. Regardless, on the domain where this is defined, because you can only take logarithms of positive valued expressions, the derivative of this, regardless of what I call it, dy dx, is going to have a lot in common with this, but it's just where the upper function has an x, and we have an x here, this lower function here has a whole inner function. And so you can think of that as a secondary function like f of x, or you can call it u, or you can call it whatever you want. But this inner expression, last class at the end, I called it just like a star. This is log base 4 of something. So its derivative is going to be 1 over, well, there's an x here and an x there. Same sort of idea. I'm going to have this trinomial here. I'm going to have a long function here. 7x squared minus 6x plus 1 times natural log of 4. So there's just one additional factor. And on this one, so you can see it's, instead of x, I've got this trinomial here, but so far it's exactly the same as before. The only other thing I need to do is, this is, I think I said last time, I always call it the chain rule factor. It's the derivative of that internal function. It isn't just an x, it was a whole second expression. But that second expression, the way that I said this was, well, it's order of operations wise, it's the first thing we would deal with. So we are actually concerned with its rate of change with respect to x, because we'd be substituting a value for x into that spot, into that trinomial. So I'm going to multiply this by the derivative of the part that I have squiggled under, the derivative of this trinomial, 14x minus 6. Now, I could write this as times and then 14x minus 6 as a second factor out there. But what I'm going to do is write it into the fraction, which is typical for how you might see things simplified into answer keys. 14, besides the fact that I'm out of room, x minus 6. Besides the fact that I'm out of room, just the way that we multiply fractions, I'll write it down here. 1 over 7x squared minus 6x plus 1. And I do need parentheses to get that whole trinomial multiplied by natural log of 4. Otherwise, it would just be plus 1 times the natural log of 4. And I don't want that. I want the whole denominator. Like this whole x is multiplied by natural log of 4. I want this whole other expression multiplied by natural log of 4. And then times the derivative of this internal first function in terms of order of operations, 14x minus 6. So this might be a way that you could write it, but because it's just a 1 on the top of the fraction here, and this is over 1, it's easy to combine, and you'll often see in like answer keys, check your work, that they'll just combine things like that because it doesn't involve any actual multiplication. It's just multiplying by 1s and sticking some things together. So sort of as a simple simplification, or if you're kind of out of space like I was, you could write this like this, or you could write it like that, but please don't go through and distribute or try to factor and reduce or anything fancy like that. But if you do see just like a times 1 where you can make it look a lot shorter, feel free to do something like that. So in general, for your mastery test, I don't want you to be simplifying, doing a lot of algebra, but things like that where it's not changing any numbers or making it look a whole lot different, that's fine. So in any case, either of these two expressions are the derivative of this y here. So I'll name this one down here as well since I don't have it next to anything. So for this y equals log base 4 of trinomial, the derivative is, well, 1 over that trinomial times natural log of 4, just like log base 4 of x was 1 over x times natural log of 4. It's just got this extra rate of change appended, the rate of change of that inner function, the part that was this trinomial. Because in terms of order of operations, the first thing you do, if x is changed by a little bit, that trinomial would first change by a little bit, and then that would cause the log function's value to be changed by a bit. That's a product of how much the first step in that changed times how much the second changes with respect to the first. So let me do a different example, different sorts of functions, some trig functions. Let's say I have y equals tangent of x, which sometimes when it's just a simple x, you won't see parentheses around the variable as that's the input to it, but it's going to be messier in a second. So just as a good practice, it never hurts to put parentheses around that argument so it's clear. But what's the derivative, just off your sheet, for y equals tangent of x? dy dx equals, yeah, secant squared of x. And we talked about this one at the end of class last time. We proved this by using quotient rule. It wasn't quite the end of class, about 20 minutes before. So secant squared still of x. So if I have, instead of tangent of x, if I have a function, let me call it f of x, equals tangent of the square root of x. All right, well, the derivative of this f of x, I'll call it d dx f of x, just to use more notation. The derivative of f of x with respect to x involves a secant squared of something, but it's not secant squared of x. Tangent of x goes with secant squared of x. Tangent of something else goes with secant squared of that same something else. So secant squared of square root of x. But the fact that it's a square root of x is important because, like I said last time, that's the first thing that happens if you're making changes. First you'd make a change to x, and that causes a change in square root of x, which causes a change in the secant value. So the rate of change of this square root of x, you can do this with power rule, or you might have memorized it off that chart because square roots show up a lot. Just 1 over 2 times the square root of x. And that's what we need to append to this. 1 over 2 times the square root of x. So if you wanted to, you could have written that under secant squared of square root of x, because again, it's this one multiplication that's not too complex. But this way we've got, this is the derivative of the inner function with respect to x, and the outer function with respect to the inner function. So I didn't name this inner function, but if I called this h of x, then this is h prime of x, and this is f prime with h of x intact. F prime evaluated at h of x, or f, the derivative of f prime, or the derivative of f with respect to h of x as opposed to with respect to x. So let me change colors. Let's say I have y equals, let's see, arc sine of x. So another notation for that, I'm sure you talked about this before, I know it's mentioned someplace or another, arc sine of x is also called inverse sine with the inverse function notation of x. These two mean the same thing. So regardless of which notation you mean, arc sine, this is the inverse function to the sine function, meaning if this is true, then the sine of y equals x. But if I want to take a derivative of y with respect to x, I need to have y isolated like this, or use implicit differentiation, which is where the rule comes from in the first place. But arc sine of x, it's a fractional expression, it's a lovely one, right? But it's positive, yeah, 1 over square root of 1 minus x squared, right? So in terms of, I know there's some x squared minus 1s and 1 minus x squared in the sine and cosine versus secant and cosecant. The tangents have the 1 plus x squareds in them. Just as a why that is, brief thing if you want to think about trigonometry. Sine function, this is the inverse to the sine function. Sine function, you can put in anything you want, and the output's going to be between positive and negative 1. Arc sine function, you have to sub in something that's between positive and negative 1, and then you get out any sort of number. So x in an arc sine function has to be between positive and negative 1, so that's the only time that this expression would be defined. 1 minus something that's between positive and negative 1, and at x equals positive and negative 1, this would be undefined. If you remember trigonometry, arc sine functions have a lot of vertical asymptotes. Every time the sine function was 0, the arc sine function is undefined. Or not, no, sorry. I'm thinking at the tops and the bottoms, the hills of the sine function where the derivative was 0, we've got these. So in any case, our arc sine function, sine and cosine, arc sine and arc cosine have this 1 minus x squared. Arc secant and arc cosecant have the x squared minus 1s, and the tangents and cotangents in their inverse form have the 1 plus, which doesn't matter what order you write this in. So in any case, here's our basic arc sine function. What if I had, let me call it something else, k of x equals, let's see, arc sine of the natural log of x. So the arc sine of a natural log of x. If I want to find the derivative of that, I'll call it k prime of x. And you can do these chain rule things in either order. You can think first about what would happen to x first and then later. So like if I were substituting in here, first I'd find the natural log of whatever x value I use, which restricts its domain, but you don't have to make any domain statements on your derivatives. Just deal with what the general formula is. So natural log of x, its derivative is, as we said before, 1 over x. But the derivative of an arcsine function looks like this. Although I don't have arcsine of x, I have arcsine of natural log of x. So I'm going to have this expression here with, instead of an x in place, I'm going to have natural log of x in that spot. So 1 over the square root of 1 minus natural log of x squared, which you can write as natural log squared of x, but I don't think anybody really does that. I mean, it's possible, but it's not. Natural logs or any other logarithms raised to powers isn't a common thing as opposed to trig functions raised to powers. But so what we have here in terms of our chain rule, we said chain rule, the general rule for that was if I had, let's see, what do we do? G of f of x. If I want to find the derivative of that with respect to x, I find the derivative of the outer function with respect to the inner function and multiply that by the derivative of that inner function. So you can write this out. You can write out what's the f of x and g of x in this situation, if that's helpful. And this, the outer function, the g is the arcsine, or this is my g prime of f of x, g prime evaluated at f of x. Previous pages where we had, so arcsine, we have this. Now we have arcsine evaluated at f of x, so f of x in that spot. And here's f prime of x, the inner function's derivative with respect to its simple input variable x. So it is possible to have more than one level of chain rule, which I said, we'll get to that. We'll talk about more examples of that, but I want you to be comfortable with 2 before we make it more challenging. Chain rule is probably the hardest, I'd say the 2 hardest things to get used to are power rule. That's number 2 hardest thing, because power functions can look so many different ways. There's so many different types of expressions that can be rewritten into power function format. And the first hardest, number 1 on the list of hard sorts of derivatives to deal with, just in getting used to it, is chain rule. Because again, the same thing, you can have 2 or more functions intermingled with one another by composition in so many different looking ways. So it's a matter of when you see an intimidating looking problem, one of the things that you should do is take a step back for a second and say, what overall is going on here? If I were to take a variable, look at the input variable, whatever it is, x. If I were to take a number in place of that variable, what's going on? Am I substituting in a few places and then multiplying together? Do I have really product rule of messy looking things? Or do I have quotient rule? That's usually easy to identify because there's generally a fraction in place. Or when I substitute in x, do I perform one set of operations and take the result of that and do a whole other completely different set of operations, in which case that's chain rule. Yeah? No, so the part in lecture, so let me show you some examples of that, but the part in lecture will just be strictly, basically looking like things off of your memorize these derivative rules. So it'd be something like y equals tangent of x, or y equals arcsine of x, that you have to find derivatives for, or something like ones that aren't precisely on there, but maybe something like y equals, let's say, 7 over x, where you have to think, oh, that's really a power function, but just a simple one, no chain rule involved, and think of this as 7x to the negative 1, so that you can find the derivative and call it negative 7x to the negative 2, and you don't have to rewrite anything into fancy fraction form. If you want to, you can, but that's not the point of it. You don't have to make it look pretty by the end. Just find a way that you can apply one of your basic rules, no product, quotient, chain rule, or anything like that, and just use those derivative rules. So something like y equals, what we did on the first one, log base, I think I used 4 before, log base 6 of x. Your sheet doesn't have log base 6 of x, it has log base b of x. But just things of this nature, possibly with a coefficient, just so there's something to do. But 1 over x times the natural log of 6. Things where there aren't multiple steps, or something like y equals 5 to the x, which 5 to the x times natural log of 5. So these level of difficulty things are what's going to be on the lecture portion of the mastery exam. There'll be 25 of them, worth 2 points each. So the lecture part is 50 points out of the 100 points for your mastery exam. And they are just things like these short ones over here. So not anything that involves multiple steps or chain product quotient rule. Possibly, like I said, a coefficient like this 7 here, but nothing too fancy. So the ones that you're going to be doing in recitation afterward, either that Wednesday if you have Wednesday recitation or Friday or the following Monday, are longer ones. Not all horrible. Some of them would be along the level of the things that we just talked about, like arctangent of square root of x, or actually I don't know if that's quite the combination that I had before, or sine of something, or maybe even just something along the lines of a short product or quotient, something like, let's say f of x is 2x squared plus 6 over the square root of x. And it says to use product or quotient rule. Okay, well, you could do this without if you wanted to simplify functions. Here, let me put in a +1 so you can. There we go. This can't be written without products or quotients involved. So if I want to find the derivative of this would be a not lecture portion. This would be a medium level problem. Uses a lot of different derivative skills, but not the ugliest ones you've seen. So lecture will be like the simplest ones, 25 of those, and then in recitation you'll have 10 others that range in level of difficulty from like medium to more challenging, like the ones you've seen on the list of 150. There are some on there that are quite a bit messier. I'll give you another list before this weekend of some additional longer practice problems to see how you feel about those. If you can do those, you should be good. But just so you have a last practice, like, do I really know these or not? Because I know you've been staring at the 150 for a while. So just to give you a fresh set of, let's see how I'm doing, like a self-test sort of thing. Like, do I know how to do these? Yes or no? That'll be over the weekend, not to turn in just a extra practice. But back to this f of x here. If I have this 2x squared plus 6 over square root of x plus 1 as its function rule, then the derivative of this with respect to x, let's see, I've got a quotient. So quotient rule looks kind of like product rule, but it's got a denominator. That's the original denominator squared. And in the numerator, I've got 2 terms subtracted. Each term is a product of 2 pieces. So I may or may not be able to actually fit it here, but we need to take the derivative of the numerator and take the derivative of the denominator, but unfortunately, we don't get to just slap them back together in a fraction. We have something that looks more like product rule. We proved product rule in class. But in the numerator, there's 2 parts subtracted. The first part has the derivative of the numerator. The second part includes the derivative of the denominator. And each is multiplied by the original other half of the fraction. So the derivative of the numerator is just 4x, right? So I'm just going to kind of scratch work in my head. The derivative of this numerator is 4x. The derivative of the denominator is 1 over 2 root x. Don't worry about compound fractions or anything like that, like, oh, I have to simplify this. Again, we're not simplifying. We're just putting together the pieces and not doing additional algebra. Just show me that you know the calculus. So derivative of the numerator times the original denominator would be, let me do this in another color so it's not so squished together looking. I'd have 4x times that square root of x plus 1. And I don't really need parentheses around the 4x because it's a monomial, but if you do have more than one term for any derivative, you do need to put parentheses around it so that you actually have the product you intended. Second half of this involves a derivative of the numerator, 1 over 2 root x times the original numerator. So those two multiplied together, and whatever order, it's multiplication, but it does have to be after the subtraction sign. So I'm going to write this part first, just because, times, let's see, 2x squared plus 6. And sorry, this is a little squished in here. But in any case, I've got the derivative of my numerator times the original denominator minus, other way around, the derivative of the denominator times the original numerator. So the numerator's derivative's in the first half of the numerator of the derivative. The denominator's derivative is in the second half, or after the subtraction. If you realize after writing out, maybe it's like a really long expression, you realize you wrote it backwards, feel free to put a plus in the middle and a negative sign on the front rather than erasing and starting from scratch, because I know sometimes things, you're focused on one part and all of a sudden like, that's supposed to be the end of it. You don't have to. If I'd done this backward, I could say plus and then throw a negative in the front if I realize that. So just double check your work. Make sure. That's one of the things that's an easy place to make a mistake in writing derivatives is quotient rule getting the subtraction wrong in the numerator. All right, so let's take a look at the 5 questions that I had up briefly at the end of class on Monday. 1, 2, 3, 4, 5, yeah. So the first few of these don't look too bad. The last one looks kind of awful. The last one's an example of this multiple levels of chain rule or lots of things going on sorts of functions. There's a whole bunch of stuff. I see multiplication and cosines of natural logs and all that, but if you look at that last function, this is just, I didn't write c of x equals, just c of x equals each of these 5 things. The last function rule contains a couple of pieces that were earlier in the list. So let's do these in order. And we talked about things along the lines of difficulty of these first couple, maybe actually all of them a little bit. But let me go back to blue, less scary. All right, so if I've got cosine of natural log of x, again, this is all about chain rule. So this is a chain rule situation. This is not cosine times natural log of x. That doesn't actually make any sense. Cosine is a function kind of like square root. It has to have square root has to have something under it for it to make any sense. Cosine has to have something after it, like cosine, and then you have of something, just like square root of something, to have it make any sense. So this isn't a product. This is a composition of a natural log function and a cosine function, where the natural log is the inner function or first function order of operation wise, and the cosine is taken of the result of that log function. So again, these 2 factors of our product rule, they're not, one of them's a nice simple factor, generally speaking, compared to the other. But one is, this is if I have g of f of x. This is just the derivative of f of x, r sub f of x, a closed form rate of change function. The outer is, well, it is the rate of change of function g, but not with respect to x, with respect to that same inner function f of x. So, like we saw before, I know what the derivative of natural log of x is. That's easy. I know what the derivative of cosine of x is, but I don't have cosine of x, I have cosine of something else. Cosine of x, its derivative is negative sine of x, right? So cosine of something else, I'm going to have in the derivative rule, negative sine of that something else, natural log of x. But the fact that it is natural log of x and not just an x is important. I need to multiply by the derivative of this inner piece here. Natural log of x, its rate of change function or derivative is 1 over x. So the derivative of function c of x is negative sine of natural log of x times 1 over x. Or you could just put that sine function expression all over x if you wanted to. Again, the ones in fractions, if you like to combine those because you do, like I do, you can write it over, but you don't have to. And it's kind of easy to see. Oh, it matches up with our rule. Here's the rate of change of the outer function g with the inner function still intact, or of that f of x, it's still a composition, and then times as a separate factor the derivative of that inner function. So one mistake that students do a lot with something like this is say, oh, it's negative sine of 1 over x. But if you think about with your sine and cosine functions, the way that they're listed on the sheet, if you take a derivative of a sine function, it's a cosine function, but the variable doesn't change. Sine of x's derivative is cosine of x. Sine of something else's derivative is cosine of that something else. Well, if it's a complex something else, then we need to use chain rule. Tag on a multiplied factor that explains how the inner function changes. But when you take derivative of sine of something, cosine of something shows up in the result. Or if you take the derivative of cosine of something, negative sine of the same exact something shows up in the end. And power functions work the same way. The base of the power doesn't change. Let's see, but logarithm, other way around. So here's an outer function that's trig and inner logarithm. Here's an outer logarithm and inner trig function. but it doesn't work much differently. I can think about this part first, or I can think about the log function first. Either way, but I've got a logarithm of a sine function. This is not multiplication. Logarithms are another thing. They have to be of something in order for them to make sense. So a log base 5 is a 1 over x times natural log of 5. If it was just log base 5 of x, this would be my answer. But it's not log base 5 of x. It's log base 5 of sine of x. Here. So I have 1 over sine of x times natural log of 5. Or it's 1 over whatever's in here times the natural log of the base. And then, as an additional factor, derivative of sine of x, cosine of x. And again, you can put the cosine on the top if you want. But in any case, this is our chain rule with that question. Here's a power function as an outer function. I've got not x squared, but I've got this expression inside parentheses squared. And why I say this is a power function, that's like the last thing order of operations is, and then square everything. So, overall this is kind of like x squared, it's just more complex. If it was just x squared, the derivative would be 2x to the first power. But it's something else squared. So our derivative is going to be 2 times that something else to the first power. So 2 times square root of x plus e cubed to the first power, which you don't have to write first power if you want to write that, for keeping track of the fact that you did actually do something. You didn't forget to write the exponent. It's a 1. But since this wasn't just x squared, I don't get to stop with that factor. I have one more factor, the derivative of the inside. The square root of x, we talked about, that's that 1 over 2 times the square root of x as a quick rule. 1 over 2 times the square root of x. What's the derivative of e cubed? 0. Yes, why isn't it e cubed? Yeah, e to the x has itself as its derivative, but e cubed is just a number. There's no x's in it, so it's rate of change with respect to x. There isn't an x. It's not changing when I change x. E cubed stays as e cubed. So I could write plus 0, or don't. Plus 0 doesn't change anything. Up to you, but we do have 2 times this expression times 1 over 2 root x. All right, so let's see. What about this 6 times 7 to the tangent of x power? Well, this 6 doesn't have any variables in it. I could use product rule because I definitely see a product. But notice that one of the pieces of the product doesn't have any x's in it. So I could also just, instead of doing that, it won't make your answer wrong, it just makes it longer looking. Instead of using product rule, I can think, oh, that's just a constant multiple. It's like a coefficient. By the way, I think we talked about this before, but this isn't the same as 42 to the tangent x power because 6 is just to the first power. So exponent rules, I can't combine those two pieces. So this, I can only write like this. I could write, instead of a dot, I could write parentheses or something, but I can't combine the 6 and the 7 in any way. That 6 is just a coefficient, essentially. Or y equals 6 times 7 to the tangent x power versus y equals just 7 to the tangent x power. That factor of 6 just makes the function's graph 6 times as steep, or the y value 6 times as large. It just increases the derivative by a factor of 6. So let's see. So I'll just copy down that coefficient, and then I'll worry about the rest of it. So 7 to the tangent of x power. Well, 7 to the x power is the basic idea of this, but I've got an inner function, so this does involve chain rule. I've got an exponential function, 7 to the x, not e to the x, as the outer function, with an inner function of tangent of x. Well, 7 to the x's derivative is 7 to the x times natural log 7. 7 to the tangent of x is itself, for its derivative, times the natural log of 7. So this is the g prime of f of x portion of this. So we've taken the derivative of the exponential function and left the inner function, the tangent function, intact. I still need an extra factor for the derivative of that tangent function. Derivative of tangent, as we said earlier, was secant squared. It's tangent of x, so I have secant squared of x. And this is our whole expression. There's no addition or subtraction in this, so I don't have to write any parentheses around it to keep it all fully multiplied together. But just make sure if you do have addition or subtraction, multiple terms in any of the pieces of your derivative, put parentheses around it if there's also multiplication so that you don't accidentally have something like 4 times x squared plus 6 or something like this, and you meant for it to be 4 times the whole quantity, because these two are not identical. So it's easy to write dots, but if you have addition or subtraction, realize that in order to indicate the multiplication you probably mean, you want to put the expressions in parentheses. Question? Right, so if it was just 6 times 7 to the x, we wouldn't need chain rule. We've just got a coefficient, that constant multiple, and 7 to the x, the exponential rule for how to do derivatives. But since I have 7 to the whole formula, 7 to a whole other inner piece here instead of just an x, that's why we need chain rule on this one. So that's where this other part comes from. So again, don't compress the chain rule and make it 7 to the secant squared of x. Just like if you have the derivative of e to the x, you see e to the x in the derivative. Or 7 to the x, it's 7 to the x times log 7. But if I have 7 to the something, I'm going to see the same 7 to that same something in the derivative, along with natural log of 7. But when that something, that exponent, is more than just a simple variable, we need to multiply by the derivative of that as well, because that does impact the rate of change of the eventual outer function. So let me scratch out some of this work here and rewrite what we had just real quick. The two pieces here that we worked on, because if you see in this last function, I've got 6 times 7 to the tangent of x and cosine natural log of x underneath a square root. So yeah, question?
So on the exam portion,
Mhm.
say if we mess up one part like in cosine on
Mhm.
x and we don't put the negative, would that just be a 0 out of 5 for that, or would it be just
So
partial credit?
yeah, so the questions we're going to do in here are very short. You either get them right or wrong. The ones that are longer, like these, there's partial credit available, depending on how bad a mistake you made. Like if you didn't know what the derivative of cosine was at all, versus just for getting a negative sign, that's different numbers of points. Yeah. So, like if you just wrote cosine of x, whatever it might be, the severity of your mistake there's partial credit available. There's 10 questions, 5 points each, so you can have different numbers of points out of 5 for each of the 10 questions you're going to do in recitation. But yeah, for the ones in lecture, it's either right or wrong. So there's basically one rule to follow, sometimes a coefficient, but there's just, you either got it right or wrong. So it's half and half between the two portions of the test, 50 points from the lecture portion of easy but many questions, and 50 points from the recitation part of fewer, but at least sometimes more challenging questions. All right, so let me clear off some of this stuff and rewrite the parts that we're going to need. So we worked on earlier, if you look at this expression here, a square root of something. If it was just square root of x, we have a rule for that. If it's square root of like x squared plus 5x plus 2, we can just do chain rule. But I've got square root of some expressions that we said earlier involve chain rule. So I've got a square root of, for instance, a cosine function, which is of natural log of x. So I've got 3 levels of functions here. I'm not going to try to write out a specific, what do you do for 3 levels of compositions of functions? But we've got addition or subtraction in between there. We can do the same sort of thing though. So let's see, cosine of natural log of x, I'll jot that down up here. We said its derivative was negative sine of natural log of x times the derivative of natural log of x. Or 6 times 7 to the tangent of x power. We said, I'm going to write this up here, so I have more room down below. 6 times 7 to the tangent of x, repeat the same exact function, times natural log of 7. This is for the exponential part, and then for the chain rule part, times the derivative of this exponent, secant squared. And it was tangent of x, so secant squared of x. So again, if it's just a simple, like an x or something, sometimes you will, sometimes you won't see parentheses around it. It never hurts, but it's not necessary if it's just a single x or t or variable like that. Now, since we have derivative of some of the component parts already worked out, this chain rule shouldn't be quite as bad, but kind of working from the outside in. You can work from the inside out or the outside in when you're thinking about chain rule sorts of things. The order of operations wise, if I were substituting in things for x and trying to evaluate this, the last step would be just the square root, right? And then once I have everything evaluated underneath, and then I take the square root. So I can't separate this into two square roots subtracted or anything like that. But then I take the square root. So the square root is the outermost function. So according to our composition of functions, the outer function, g in this is, I take the rate of change of that function g, leave the inner intact, regardless of what it might look like. So I'm going to start writing this up here. Square root function, I have 1 over 2 times the square root of x, if it was a square root of x to start with. I'm going to have 1 over 2 times the square root of the same exact stuff, 6 times 7 to the tangent x, minus cosine of natural log of x. That's all under the square root in the denominator. So again, square root of x's derivative is 1 over 2 root x. Square root of something else's derivative would be 1 over 2 times the square root of that something else, but times the derivative of that something else. So now we're down to the, okay, so I had the rate of change of my outer function with the inner intact. Now I need to find the rate of change of my inner function. It's just that it's, unlike the general chain rule written up there, the stuff that's inside here isn't quite so simple as it has been in previous examples. It's not just a natural log of x or polynomial or something. So I need to think about the derivative of this whole 6 times 7 to the tangent x power minus that. So what's underneath is a subtraction of 2 terms. To take the derivative of 2 terms that are subtracted or added, you just do the 2 derivatives separately and then subtract them. Luckily, we already worked out the derivatives of those 2 parts. We have them up above. Now, so this is going to be long, but it's going to be this fraction times, and I'm going to write this on the next line. And the reason I just wrote that there is not because I couldn't have just said that to you, but let's say you're taking the mastery test, you get too close to the end of the edge of the paper. You don't have to write like sideways and upside down. Just give us a hint as to, like, if you're going to write it on the next line, how is it connected to the next line? Like times here, if it was plus, and you need to go to the next line. Just, you know, an arrow or a C next line, because I realize that some of these are going to be kind of long, and you might run into the same situation I'm here. There's no way to write all of this and have it be anywhere close to visible or legible, all on one line in the space I have. So this is an example of one of the hardest sorts of functions you might see. Might be something maybe a little trickier. Maybe there's another coefficient in there or something, but not too much weirder than that. But on the next line, what I'm multiplying this by is, since the function inside here is a complex function that's composed of 2 things subtracted, I need to take the derivatives of those 2 things subtracted and subtract them. So 6 times 7 to the tangent of x power, oh, well, here's its derivative right there. 6 times 7 to the tangent of x times the natural log of 7 times secant squared of x minus the derivative of the cosine part of this. Derivative of cosine is negative sine, and we said this one was, so sine of natural log of x times 1 over x. So all this stuff down below is supposed to be multiplied onto that. This looks pretty horrifying. If you had to, so I said, what's the graph of this look like? Like, no idea. But GC does. If you wanted to check to see if you did this derivative correctly, you know what you could do. Here's our, we define this as f of x. I could define my, pick a value for h, write my r of x or r sub f of x equals this, c of x plus h minus c of x all over h, graph that, along with, if you are lucky enough to be able to type this in properly, the graph of what we came up with as the closed form function of this rate of change, and see if the graphs overlie one another. If they do, you did it right. If they're completely different shapes, then there's something wrong. It could just be parentheses, which is something important. If you had the parentheses written but you didn't type it, that's a different thing. But if you had parentheses in the wrong part and it makes a big difference, then clearly those are important parentheses. But I understand this is a mess. This is not easy, and this is not something that c of x equals this lovely thing. I don't know precisely what some applications of that might be, but theoretically speaking, we have all the skills to find derivatives of anything at this point, just about. There's a couple things we haven't talked about yet. But we can find the derivative of this with respect to x, the variable that's the input variable to this overall. It just takes a lot of work. You have to focus on lots of different things here. So we've got outermost, we've got a square root. If we work inward, I've got two things subtracted. One of those things subtracted was an exponential function that had inside of it a trig function. The other half of the subtraction was a cosine function that had inside of it a logarithm function. So there's three levels of things going on here, in addition to the fact that there's a subtraction involved. But just, if you can either work your way from the outside in or the inside out, this is thinking outside in, square root function, and then what's under the square root. I could work the other way around too. Think about what's the derivative of the stuff that I see underneath, and then realize that that was all under a square root, and so do a 1/2 root of that afterward, whichever way makes more sense to you as you're thinking through this. But again, take your time. There are some things approximately this level of difficulty on that list of 150, not too many. But as I said, I'll give you some additional practice at some of these longer ones, some like medium and hard ones, as opposed to just polynomials or something, for over the weekend for extra practice. If you have questions that way about any of those, we're not going to go, it's going to be more than we can go over in class. So we'll go over, if you want to head to office hours, things like that. Make sure you can go to, for additional assistance, any math tutoring center anywhere in the country, because everybody knows derivatives just as well as anybody else. So it's all the same derivative rules, no different terminology or anything that's going to make somebody say, I've never seen this before. If they haven't seen it before, then they have definitely not taken calculus. So in any case, so hit up our office hours, hit up any of the tutoring center hours anywhere, and study well. But I will see you on Wednesday. We'll go through a few examples, and then we're going to talk about some other uses of these.